let's do this. Here's another sequence. Sequence is a list of numbers with a set pattern. A series is when we add those together. So let's find the next three terms. First of all, let's find the pattern. The pattern is 1/3, 1/9, 1/27. Okay, well, it looks like we're multiplying the denominator by 3, which really means we're multiplying by a third. Let's word it another way. We're dividing by 3. 3 ways of wording it. You're multiplying the denominator by 3, you're dividing the entire term by 3, or you're multiplying by 1/3. So I believe it's good for us to just walk over here to the side with the blue marker and call this what it is, and this is going to come in very handy later. This is a geometric sequence. And geometric is when I am multiplying by the same thing every time. In this case, I'm multiplying by 1/3. So multiplying to get, I want to word this very well. Multiplying by a constant to get the next term. And that constant is, and this is going to work out later as we proceed through this unit, that constant is called R for common ratio. So multiplying by a constant, and that is R, standing in the way so you can see. So now you can see. Multiplying by some constant R. And in this context, R is 1/3. We're dividing by 3, which means we're multiplying by 1/3. So just good to know R equals 1/3. There we go. So find the next three terms. Let's basically divide by 3, divide by 3, divide by 3. And when we do, we'll see that the next three terms are 1/81, because we're tripling the denominator, 1/243, and then 729? Yeah, 729. So those are the next three terms. Let's write the explicit formula. Okay, guy walks up to you, hands you this pattern, first three, and he says, all right, what's the fourth term? Easy. Find the pattern, go to the next one. And he says, okay, what's the fifth term? Easy. Go to the next one. Sixth term, easy. All right, what's the 100th term? Whoa, wait a minute. Now we did this for the arithmetic sequence. Now we're going to do this for the geometric sequence. So if I want to figure out how to get to any given term, the nth term, then I need a few things. I need to know, first of all, what I start with, which is fairly obvious in this case. And what I'm starting with is the third. And then how do I get to the next term? Well, I would multiply by 1/3. Okay, these are two different 1/3s. This is my first term. This is my common ratio. So I start here, but this is what I'm multiplying by every time. Total coincidence that these are the same number, all right? Total coincidence. So if I wanted to go to the second term, I would do my first term times the third, and it would give me 1/9. If I wanted to get to my third term, then I would take my first term and multiply it by itself 2 times. If I wanted to get to my fourth term, then I would take my first term and multiply by common ratio, common ratio, common ratio. I'd have to do this 3 times. So for any given term that I want, I would need to multiply by my common ratio that many times minus 1. Minus 1 because we already had a starting point. So the nth term, I almost wrote A, we're going to call it B. Call it what you want, but the directions on the paper say call it B. So this sequence called B has an explicit formula of B sub n, the nth term, whatever term I'm looking for, would be 1/3. This is my first term, multiplied by my common ratio raised to the n minus 1 power. Because again, that's how many times I would have to multiply to get there. Let me kind of pause that and use an example that's a little more, it's a little easier for us to wrap our minds around because there's so many 1/3s floating around here. I'm going to switch colors. Let's go blue for just a second. If I had a completely different list and it was 2, 6, 18, 54, same idea. Let's do it again. If a guy walks up, hands you this, says, what's the 100th term? You don't want to count all the way to 100. You wouldn't have to because you already started with the fourth one. but you would have to be like 5th one, 6th one, 7th one, 8th one. Not worth it. Totally not worth it. Okay, where did you start? And what did you multiply by? You multiplied by 3. How many times would you multiply by 3? Depends on what term you want. If you want to get to the second term, you'd only have to multiply by 3 one time. If you want the 100th term, you'd have to multiply by 3 100 minus 1 times. So there it is. So that's a different one, different example. Let's come back over here and let's write some things down. The explicit formula for a geometric sequence is this. Knocked the cord off. Whoa, wow. Knocked that thing crooked. There we go. Let's fix this thing. And crisis averted. A little crooked, but yeah, we'll keep going with it. All right, A sub n, why A? Because I felt like it, but this one's B. It doesn't matter. It doesn't matter. I'm giving you just the general formula, and the general formula can be A, it could be B. I'm just going to use A. The general formula for the explicit formula for a geometric sequence is first term, A sub 1, multiplied by R, the common ratio, and I would raise it to whatever power, whatever term I'm looking for, minus 1. So n minus 1. That is the explicit formula. That's going to come in very handy. All right, so let's ignore this one. This was not the example we were doing. Just wanted to prove a point. Limit as n approaches infinity of b sub n. In other words, if I wanted to, let's do that. If I wanted to rewrite this, I could have the limit as n approaches infinity of 1/3 to the n minus 1. Okay, we had a lesson a long time ago called limits at infinity. This is a very similar idea to that, and we're going to finagle this a little bit, and we're going to do some mathematical magic on this, mathematical trickery, if you will, and we're going to need some of those skills as we learn to rewrite some things later on in this unit. In the meantime, here's the big question. As we continue to write these, if your task all day, write the next term, write the next term, write the next term, write the next term, write the next term. As you do that, what number is it approaching? Like as you write the next term and then the next term and the next term, you're like, man, these terms are really approaching what? Okay, 1/3, 1/9, 1/27. Clearly they're getting smaller because the denominator is getting bigger by a factor of 3 every time. So this is approaching 0. Let me show you a little bit in a different context here. Because, and this is glorious the way this one specifically works because these are both 1/3. Because these are both 1/3, I can put a 1 here, it's already there, and then add my exponents, 1 plus n minus 1, and this really gives me the limit as n approaches infinity of 1/3 to the n, and this is the glorious part. I can continue rewriting this, and so I have the limit, maybe not necessary, but you know, it's fun. N approaches infinity of 1 to the n, well 1 to the n is 1, over 3 to the n, okay? I have a huge denominator, right? 3 to the infinity, that's big, so this approaches 0. Now we probably could make an argument here that technically I have 1 to the n and then 1 to the infinity, and that's indeterminate, and then we end up in a L'Hopital situation. But we know what happens. We can kind of see the pattern here anyway. It's approaching 0. Okay, I'm going to erase some stuff because I want to find S1, S2, S3, S4, and I want to explain what that means. And we did in the last problem, but in this problem, same idea, but it's going to be done a different way. Okay, so in the last problem, excuse me. Sorry, I had to hear that. In the last problem, and mute it now. In the last problem, we had a pattern to it when we were trying to figure out the sum of a sequence, sum of a series technically, because if we're adding them together, it's a series. So as we did that, there were patterns, and we'd be like, oh, first one plus last one. And that was great when it was arithmetic. When it's geometric, it's a completely different formula, totally different. And we're actually going to, I'd love to put it over here on the side, but we're going to get to that later. That's going to be its own separate thing in a separate lesson altogether. In the meantime, we're just going to sort of look at some patterns and see what's going on. So, crowded board, going to erase, and last two questions for this section. Find S1, S2, S3, S4. That means find the sum of the first one term. That's lame. Okay, the sum of the first one term would be the first term. That's lame. Done. All right, the sum of the first two terms would be 1/3 plus 1/9. And we're doing this so we can kind of sniff out the pattern. And this is going to give me 3/9 plus 1/9, which is 4/9. Okay, good to know. S3 would be 1/3 plus 1/9 plus 1/27. Well, let's cheat a little bit, just a little bit. You already know what 1/3 plus 1/9 is, so you may as well put it. So these two together make 4/9 because you already found it, right? And then plus 1/27, and then we can go from there. And you're like, let's just grab a calculator. It's good to do this by hand, sniff out patterns. So 27, let's just do it this way. 1 there, multiply by 3 is going to give me 12. So 13 over 27. I'd like to look at the pattern at this point. So 1/3, okay. 4/9, okay. 13 over 27. Okay, so clearly they don't reduce. But if they were close to something that would reduce, what would they be close to? That's the question. You'll see it in a second. S4 is first term plus second term plus third term. That's not a 3. That's a 27. Third term plus fourth term. All right. Nobody wants to do all this work because you already found the sum of the first three terms, so let's do it. It's 13 over 27 plus 1 over 81, and we'll keep going with that. Common denominator is 81, so put a 81. That one does not change. We would triple the 13, gives me 39. 40 over 81. Okay, the question earlier was, what does this approach? What does the sum approach? This is a different idea than saying, what does the sequence approach? What is the infinitieth term, so to speak? The limit as n approaches infinity of the explicit formula. That's a different idea because as I go forward, like I said just a few minutes ago, I would be approaching 0 just by listing terms. But by adding them, what am I approaching? 1/3, 4/9, 13/27, 40 over 81. So here's the other question. This doesn't reduce, but if it did reduce, if it was close to something that reduced, what would it be close to? And we're going to actually answer that when we go to the next problem. So, does the infinite series converge or diverge? First problem we did, it diverged. It was like, I forgot the numbers, but it was 5 plus 11 plus 17 plus 23 and plus 29 plus 35 plus 41 plus big plus bigger plus bigger plus bigger plus bigger, infinity, right? 1/3 plus 1/9 plus 1/27 plus 1 over 81. And as we do this, we're getting a fraction that's within certain boundaries. It's not going to be expanding in a crazy way. It's not blowing up on us, right? So like in layman's term, this number is not like, getting super huge. It's really just going to converge. Okay, I don't have an explanation for this without giving you a formula, and I don't want to give you the formula yet. Again, the purpose of this was to sniff out the pattern. What is this very close to? 40 over 81. Okay, what is it close to? Let's find out. I'm actually going to do the next one just because I want to. So S5, and it's going to become a lot more obvious on this one. That would be 40 over, you don't have to write this, I'm just having fun at this point. And the next one is 81, that would be 243. 243. So 1 over 243, which would give me 243 is the denominator, and triple that is going to give me 121. 121 over 243. Okay? What's that close to? Let me show you. And don't do this because it's illegal. What's that? That's a half. We're not that far from a half. So does the infinite series converge? Yes, because as we continue this process, they're not blowing up. They're not getting way far out of bounds. We will deal with this idea a lot more later. But what does it converge to? Find S. Whoa, S, just S, not S1, not S2, S. This letter, capital S, is used to show an infinite sum. So the sum of everything. If I at, excuse me, hard for me to say. And don't pat the microphone either. Whoop, whoop. 1/3 plus 1/9 plus 1/27 plus this, plus this, plus next, plus next, plus next. forever, for all eternity. It'd be a waste of your eternity, so don't do that. But if you did, you would end up with 1/2. Find S, it's a half. Here, S equals 1/2. Capital S, the infinite sum of all those terms is 1/2. And that was not the off button. This is the off button.